Hi everyone, welcome back to Workshop, and it's repair time again, and another HP 344018 6.5 digit multimeter. Now this one, as you can see, is in nowhere near as good cosmetic condition as the last one that I repaired, but I couldn't resist this one. The photographs that I was shown of it in operation showed a clear fault. All the digits were basically on in display. There was no numbers at all. It was just all segments on. So I thought it'd be a nice candidate for repair, and we're going to tear it down. We're going to have a look inside. I'm hoping that the internals are in a bit better condition than the outside. But before we take it apart, let's take a look at some of the stickers on the unit. SE Laboratories NXP0061. SE Laboratories are a calibration / repair house, so I can only presume that the meter went to SE Laboratories for calibration. And on the top we've got a calibration not required sticker, ST Ericsson. ST Ericsson were a company that ran between 2009 and 2013, consisting of Ericsson, the phone giants, and ST Microelectronics. So looks like perhaps the meter was used by ST Ericsson, and maybe they farmed it out to SE Laboratories for the calibration. The only other sticker that's on it is a functional verification sticker. Thank you very much, Marianne G, for looking after this meter. So let's open it up and take a look inside. Now this meter doesn't have the rear panel, but I can get them on eBay. They are readily available, so I'll see if I can pick one of them up, because I do like the meters to be somewhat complete. Okay, and here we are inside the unit. It looks clean enough, which is to be expected. These units don't have fans, and there are some differences between this one and the previous 344018 that I repaired. The first thing that struck me when I looked inside this one is, here's a ribbon cable that goes away off to the display board. On this one it's soldered directly onto the circuit board. There's no socket there, which is a little bit of a pain, because it's really handy to be able to disconnect the display, especially when you're repairing the main board, etc. The other thing I notice is this is a Rev A board. The last one was a Rev B, so I'm not really too sure what the differences are, but there is bound to be relatively minor. Everything looks fairly intact. I don't see anything blown. There's perhaps some staining on the top of this cap here. Nothing's bulging, but per the last 344018 that I repaired, there was some hidden damage to the caps on the underside. You couldn't see it, so I will be replacing all 4 of these large electrolytic caps as a matter of course anyway. Turning the meter over, I'm not too sure if somebody's been in this meter before, but looking at this row of pins here, this is the little ribbon cable that goes off to the display, and this has definitely been resoldered at some point in its life, and it looks to be quite a long time ago that it was done, because I haven't made that good a job with it, but you can tell that the quality of the flux that was used wasn't that great, and it's left a lot of crusty residue there. Similarly, over on the front rear switch here, this looks like it's been resoldered as well. Now you might be forgiven for thinking that, well, maybe this switch was fitted later on down the line, perhaps after the main assembly of the board had been done, but I don't think so, because in actual fact it's quite important to keep this switch clean. This is basically the front rear switch. Everything goes through this switch that comes from either the front bananas or the rear bananas. So with flux and residue like this, you're not doing yourself any favors in terms of microvolts, etc. The other thing I can see here, let me zoom in on this part. And what we've got here, it looks like there's some kind of repair job being done on these tracks here. There's a lot of flux residue on there, and without cleaning it up to have a proper look, I'm not really sure if perhaps those tracks had been you know, damaged, or perhaps cut, and this is some sort of repair job to try and fix that. Whatever they've done, it's not been too great a job. Again, these are the signals coming from the rear bananas, so you want to get rid of any flux residue as much as you can. So I will be taking a look at that, and of course I will be cleaning up all the flux residue. Right, before I tear it apart, it's time to power it up and see what the actual fault is. It's already set for 240 volts, so let me go away and hook it up and I'll come back. Okay, ready for power up, so let's go for it, see what happens. Wow. Okay, hopefully you can see that, but all segments are lit on the display. And importantly, I'm not hearing a beep from the meter, which signifies that the main processor's up and running. So let's switch it off and try that again. Just all segments on, then nothing else. Now, from memory, on the HP Agilent power supplies that are repaired, if I remember with those, the microprocessor on the front panel is responsible for setting all segments on, as you see there. It's then waiting for data from the main board in order to get something on the display. So my gut feeling at this point in time is that perhaps there's a problem on the main board and it's not starting up. So let's reposition the camera, let's take a look inside it again and start measuring some voltages. Okay, we're ready to test some voltages. So what we've got here is an LM317 and an LM337 down here beside these two large electrolytics. That's a plus and minus 18 volt supply. We've also got out of sight down here, we've got an LM2925. That's the 5 volt regulator for the entire logic area there. And over on the GPIB section, which is isolated from the main logic section, there's a 5 volt regulator down here, which supplies 5 volt to the microprocessor and the GPIB chip, etc. So let's measure those and see what we've got. So we'll find a suitable 0 volts. I think I'll get that down here. And we'll go to the positive 18 volt supply first, which is pin 2 of the LM317 there, and 18.8 volts DC. So let's just see what ripple we've got, and I'll put it on AC on the meter there. Let's take another look at that, if I can get a good connection. There we go. And there's not that much ripple there, so that's okay. So let's get back and look at the negative 18 volt supply. That's pin 3 of the LM337. Oh, get a good connection again. Minus 18.2, and let's take a look at the AC component. And it doesn't look too bad either. So those electrolytics are probably functioning okay, those large capacitors here, but I will be changing them out anyway. Now let's take a look at the 5 volt supply to the main logic board. I'll just go across that RAM IC down there. 5.02 volts, that's pretty good. And whilst we're here, let's just check the ripple there. And it's not bad at all. So the main logic area supplies look to be okay. There's definitely none of them have dropped out. So here's the schematic for the power supply. You can see the transformer down here, and you've got 3 separate bridge rectifiers coming from different windings on the transformer. You've got a bridge rectifier up here which produces the plus and minus 18 volt supply. Got another bridge rectifier here, which is producing the 5-volt logic supply for the main board. There's the 2925 there. And you've also got down here another bridge rectifier with the 5-volt regulator on the earth referenced circuit power. And that is the GPIB section there. Now there's the 5-volt regulator just right down in there, and unfortunately it's a surface mount part, so I can't get it from the underside, so I'm going to have to probe through some holes on the side of the casing here. If I can't get that, I'll obviously have to take the board out, but for now let's just try and see if I can't get access through the side of the meter here. And we've got 5.07 volts, so the GPIB section is indeed getting power. Let's just check the AC component on that 5-volt supply, and it's very little if any, so that looks to be fairly stable as well. Okay, with all the power supplies intact, it looks like I've got no choice. I'm going to take the circuit board out so that I can get to it a bit easier. Right. Okay, first things first, I'm going to take off the 2 red tabs. They just get in the way and don't allow the front panel to come off at all. So I think I showed this in a previous video, and these are little plastic catches that hold on the front panel under there. There's a little loop on this plastic catch that grabs the front panel. Similarly, you can see it quite a bit easier on the rear one here. It's exactly the same catch. It snaps into place here, and you can see it's hooked onto the back panel there, so you can't actually pull the board out, and you've got to remove these before you can disassemble the meter. And the way to do it is, let's take a look. What you have to do is, you can spend all day trying to pull it up and push it down. The problem is you can't pull up because it's hooked under there. It's not going to do anything pushing it down. What you actually have to do is bend this plastic tab by pushing down on here. You can see that it's now releasing the hook that goes onto the back of this plastic part here. But the problem then is you're then forcing up the hook that comes onto the front panel. So what you have to do is pull up here and push down there at the same time. So you have to deform the plastic catch in order to get it out. So let's do that now. Not easy. I think the one in the rear is actually easier than the front panel one, but we'll... That's it. And that's it there. And you can see the hook there and the hook there. They're both identical. This one's a lot easier to get out normally. There we go, and that's it out. Now, to get the front panel away from the chassis requires another little trick. The problem is, on the side of the chassis here, there are some bosses that stick proud of the chassis and go through 2 holes on the front panel, so you can't just pull it off. So what you have to do, I found easy, is just to put a screwdriver down the back there and just deform the chassis inwards slightly, and as you can see, it then allows it to pop up. Now the other side's a little bit harder, and the reason for that is you can't deform it very easily because the plastic push rod for the actual front panel goes down the side in there and stops the chassis from moving inwards. There, that's the push rod out, and that will allow the chassis to deform at this side as well. That's it. That will allow the front panel to release. Unfortunately, this ribbon, as I mentioned earlier, is soldered to the board, so I'm going to have to watch that, or I'll end up replacing it. And from there, I can just unplug the various connectors. And I should be able to slide the board out once I've removed the screw here. One screw at one side holding it in. And that's it. The board is now free. Okay, the first thing I'm going to do actually is replace those electrolytic capacitors. Let's just get on a good footing before I start troubleshooting the board. The other thing I've gone ahead and done here, a little trick, I'm a bit dubious about moving this front panel around and putting any stress on the cable as it goes through the circuit board here. So I've actually put a tie wrap around it. Let me just zoom in. I've actually put a tie wrap round the ribbon cable and round the connector that's conveniently situated right next to it, so that'll stop it from bending back and forth and possibly snapping those connections there. Not a big deal if I do that, but I'd rather not given the length of this ribbon. Right, looks like I need 3 different sizes of electrolytic capacitor there. 25 volt 4700 on the GPIB section. We've got 2 1000 microfarad 50 volt on the plus and minus 18 volt supply, and we've got a 25 volt 2200 microfarad on the 5 volt supply. So I've got my stash of electrolytics here. Let me go and have a rummage through, see what I can find, and I'll come back once I've soldered them in place. Well, that's the capacitors changed out, and actually I got a couple of nice Panasonics there to replace the 2 across the plus and minus 18 volt supply, so that's good. And I thought I'd take a look at the flux residue that was on the back of the board here. I've managed to clean it up. I did actually have to use a little bit of acetone and then go over it with some alcohol afterwards to clean them up. And as you can see, it's pretty clean now. And yeah, the soldering's not that great on the ribbon that goes away off the display. However, looking down on here, it looks like they've done a repair job on these tracks previously and then used some sort of varnish just to cover it. By the looks of it, you can see the varnish there. I mean, acetone and alcohol didn't touch it, and yes, it does look very much like transformer varnish that's been put on there. I don't think the tracks were cut intentionally. I think it's probably just a flaw possibly during production, and maybe this is just how they repaired it back at the factory. Maybe the board got dropped and it scraped across those 3 tracks there, so they took no chances in doing some sort of repair. But I don't like the idea of having 20 or 30-year-old varnish across basically the tracks carrying signals from the bananas. So I'll just scrape it off as best I can, and then I'll just re-tin it. There's no wire being laid along the track, which is quite often done to repair tracks. It just looks like it's just been packed with solder. And a little bit of alcohol just to clean it up. And dry it off. There we go. And I'll just lay down some solder. and I'll just clean it up. And there we go, it's all cleaned up, so I'm just going to leave it like that. I didn't really see any gap or cut in the tracks, so whether it was just a scrape that they just took a precaution and just cleaned it up, I don't know, but I'm much happier with that now. Got rid of that varnish. Okay, here's my setup, nicely laid out in front of me for probing around with the oscilloscope, the multimeters, and I got a good view of all the components. I've got the display hooked up, it's on its end here so you can't really see it, but I can see it no problem at all. I've got the chassis hooked up, and I've managed to get the secondaries hooked up to the board, and the power switch is right there on the internal of the chassis, so I've got good access to that. Okay, first things first. With all segments on in the display and no beep coming from the GPIB microcontroller, I'm going to look at the main microcontroller on the main board. I've identified that the supplies all look okay. I want to first of all take a look at the reset pin on that microcontroller and let's see what it's doing. So on the scope now. Okay, and the pin we're looking for on that microcontroller is pin 16, so I'll just go on it now. 10, 11, 12, 13, 14, 15, 16. And look at that. Reset's being constantly pulsed by something. No much wonder that main microcontroller is not starting up properly. So let's take a look at the schematic and see where that's coming from. Okay, so here's pin 16, the reset pin on the main microcontroller that's pulsing. Following that back, it also goes to the reset pin on the main ASIC, and that's been driven from XPON RST via the small low pass filter. So let's take a look and see where that's coming from. Okay, and we're on the power supply schematic that I touched on earlier. Here is the 5 volt supply that powers the main logic area, and here's the 5 volt regulator, and it's got a built-in supervisor on the 5 volt supply, and this reset output pin from that 5 volt regulator is what's driving XPON RST. Now there's a specifications for this regulator. Basically says if the 5 volt supply goes out of spec or the IC overheats, anything like that, then it will start pulsing this output here. So what's causing that? Let's take a look at pin 2. Let's measure it more closely now and see what the output voltage is on pin 2. Right, I'm on the ground of the regulator and we'll go on to pin 2 if I can. 5.0294. That's within spec. So there must be some other reason why that output is pulsing. So here's the data sheet for the regulator, and I've used this one before. It's the same regulator IC that's on the HP power supplies, and I really like this example timing diagram that it gives in the data sheet. If you look at the left hand side here, you've got the input voltage here. In this example they're just showing a 14 volt input voltage to the regulator. You've got the output voltage 0 to 5 volts, and you've got the reset output as well, whether it's 0 volts or 5 volts. Now you can see when power is applied, eventually you'll have a steady state. You'll have the input voltage at 14 volts, the output will be at 5 volts, and the reset will be high. That's its normal state. But let's just say there's an input transient of 60 volts comes into the input, then the IC will detect that, it will shut down the 5 volts, and it will drive the reset pin low to signify there's a problem. But once that transient disappears, i.e. it goes below a certain voltage, then everything becomes steady again. You've got you return to your 5 volt output, you return to your reset pin going high. The next example along is if the input starts dropping well below the input spec. You can see in this example here it dropped down to 3 volts, therefore the output could only manage to go to 2.4 volts, and at some point during that drop the reset pin drove low again. Now the next example is if the input voltage starts jumping around, if it's going up slightly, down slightly, or there's some small fluctuations in that incoming power and it's within spec, then there'll be no problem. You'll still get your 5 volt output and you'll still get your reset pin staying high. Now if the output is short circuited, i.e. you can see it here, it's dropped down to 0 volts, but you're still maintaining a 14 volt input voltage, then the reset pin will drive low again until such time that short circuit disappears, the output returns to 5 volts and your reset pin goes high. And the next one along is thermal shutdown. So let's just say you're drawing too much current from the IC, or the heat sinking's not good enough, then even though you're maintaining a nice 14 volt input voltage, the output will drive down to 0 volts, it will shut down, and the reset pin will also go low until such time everything recovers, and then you'll get back to your 5 volts output voltage and a high. So overall, from the timing diagram, you can really see how this IC works. So here's the regulator here, and it doesn't get hot. It's got a nice 5 volt output as I measured, so something else is causing it to shut down permanently. I don't think it's a transient. I've just fitted a new capacitor there, this big one here, on the output of the bridge rectifier, and I don't really see it being a transient problem. If it was a transient problem, I don't really see it being permanent. Sure, every now and then you might get a shutdown, but not permanently. This IC is never going into a working state. It's not an output short circuit because I'm getting a good 5 volt supply. So is it a faulty IC? So what else can it be? Well, there is a couple of external components that you need to fit on it. Obviously you've got an input and an output capacitors that have to be fitted, but there also needs to be a delay capacitor on one of the pins. There's an extra pin on the IC which sets the delay on for power up. So is it possibly C3 0.1 microfarad? Problem there. So I'll go off and check those capacitors. If they're okay, then I'm going to lift that IC and put a new one in. I have got a few of these in stock. Well, changing out the regulator turned out to be a rabbit hole. So I had a look at the timing capacitor, the delay capacitor, everything's okay there. All the capacitors on the output of the regulator, the 5 volt regulator, everything's fine there as well. But still, the reset pin is pulsing away. So I thought, well, let's take a look at the schematic. So looking at the schematic, here's the reset pin coming in here. There's a small low pass filter. Then that reset signal then goes to the reset input on the microcontroller and also the reset input on the ASIC itself. So I then pulled that 215 ohm resistor from the board, therefore isolating the reset signal from the 5 volt regulator, and guess what? The pulsing is on this side. It's on the microcontroller ASIC side. It's still pulsing away. And on the other side I'm getting a nice steady 5 volt signal. So what's actually happening is there's a problem with either the microcontroller or the ASIC, and it's somehow or other back feeding a pulse back up onto the reset output of the 5 volt regulator. So the question is it the microcontroller that's got a problem, or is it the ASIC that's got a problem and it's back feeding through that 215 ohm resistor back to the reset pin on the 5 volt regulator? Don't really know, because they're paralleled up at this point here on the capacitor of that low pass filter. Then it splits. You can see a track goes from here to here, that's for the microcontroller, and then you can see it's teed off. It must go away under the ICs, away up, and then on to pin 13 of the ASIC. So I'm going to do a little test before I proceed any further. On that low pass filter, I'm actually going to stick a bigger capacitor in parallel with the 10 nanofarad one that's fitted, just to see what happens. And there it is, I fitted a rather large tantalum capacitor across that one there, just to see what effect it has on that signal. So let me try putting power on now. And you heard a beep. That was the buzzer here, and that means the GPIB microcontroller is now up and running. And I suspect it's because I'd interrupted the reset signal, and therefore it's given a chance for at least the GPIB section to begin operation. However, I still don't have anything on the display, and if I scope the signal on both sides of the resistor there, i.e. the reset signal coming back in towards the microcontroller and ASIC, it's still pulsing away, albeit it's rather damped now with this large capacitor. So it's a pretty low impedance return signal that's coming back, and even this large tantalum capacitor is not enough to just pull it. So it's no high impedance signal. It's definitely something that's got a bit of drive to it. Now the problem is it the ASIC or is it the microcontroller, or is it both? So I'm going to try and maybe pull one of the resistors there to break the connection between the 5-volt regulator and this low pass filter here, such that I can give the microcontroller a chance to power up if I can. Wow! So I just lifted this resistor here on that low pass filter to start playing about with it, and I put power on, and I thought I could smell that unmistakable smell of a tantalum about to go. And look over here, this tantalum capacitor is quite discoloured, and it is quite hot. So looks like we've got a problem over here. So first thing I'm going to do, I'm going to lift that tantalum capacitor and replace it. It's a 22 microfarad 20 volt capacitor, so I'm just going to replace that with whatever I've got in stock, and then we'll try powering up and we'll start troubleshooting around here, see what's wrong here. Okay, so I've fitted aluminium capacitor, just perfect size, didn't have any tantalums, but I'd rather use these anyway. 22 microfarad 50 volt, but what I do notice is there's supposed to be 15 volts across that capacitor. There's 18 volts, and that's for the minus 15 volt supply for the analog section, and this tantalum here is the same but across the plus 15 volts, so that one's fine. So it looks like this tantalum that was in here is gone because it's running it too close to its maximum. So the next thing to do is to find out why I've got 18 volts across there when there should only be 15. Now there is no 15 volt regulators on this board. If we take a look at the schematic, okay, and here's a schematic for the A to D converter. The board doesn't use 15 volt regulators. It uses a couple of 3.3 volt Zener diodes from the minus 18 volt and the plus 18 volt supply in order to generate the 15 volts. So if I'm getting minus 18 volts where there should be minus 15, it's probably because the 3.3 volt Zener diode is short circuit. So I need to go and find C402-A on the board. Right, so conveniently mounted next to the two capacitors are the two Zener diodes, and if I go across the one for the negative supply, you can see 0.4 of an ohm, and if I go across the one for the positive supply, yeah, we're up at 24k, no problem. So that Zener is short circuited, so I'll need to remove that and see if I can find something that can go in its place. So there's the new Zener diode fitted, A little SOD123 package which I just managed to shoehorn in there. Should do the job. So let me just hook up my multimeter here and let's get it in shot and let's see if it works. There we go. And if I go across the capacitor there, I should see minus 15 volts. Perfect. So plus and minus 15 volt rails are now working. So casting my eye across the board, I did come across this here. This looks like another Zener diode perhaps, or it could be a transistor. I'll need to look up the circuit. But it looks like it's got a little bit of a hole in it. I don't think you can see it too clearly on camera, but there's certainly a hole or some kind on that package there. So let's have a look at the schematic and see if I can't find what that is and what it's doing. There it is on the component layout. It is CR307 and I think I found it on the schematic. So here we go. CR307, it's another 3.3 volt Zener diode across the same minus 18 volt supply, generating a minus 15 volt supply. So I presume it's open circuit, so let's put the meter on both sides of that Zener and see what we're getting. That's the minus 18 volt side, and on the other side 0.7, and this is the unused pin here. Yeah, that's another 3.3 volt Zener diode that's gone. So let's replace that one now. Well, that's the Zener diode changed out, and on power up I'm getting about minus 9 volts on what should be the minus 15 volt side. So I suspect that something connected to that minus 15 volt supply is pulling it down. Unfortunately, there's loads of these little Zener diodes dotted around to produce multiple minus 15 volt supplies, or perhaps I should say fortunately, because the problem with this one hopefully limits it to just a small selection of components, and I think it's down in this area here, which on the schematic is all to do with the 50 kilohertz flatness adjust and the AC circuit signal processing there. So I'll have to look at the schematic there, and unfortunately, unless something's getting hot, I'll put the thermal camera on it. Unless something's getting hot, it's just a case of lifting components to see which one manages to restore the minus 15 volt supply. Now the way to find out which components are connected to that Zener diode is over here on this power supply side. You can see the various Zener diodes. In fact, there's 4 of them. 2 for a minus 15 volt supply and 2 for a plus 15 volt supply. So looking at CR307, which is the Zener diode I just replaced, that's minus 15A as opposed to minus 15B. So looking at the diagram here, I've started highlighting the components that are connected to minus 15A. As you can see, hopefully, those 2 components for a kickoff, but it is dotted around. You've got U304 here, which looks to be an analog switch perhaps, and probably some other components dotted around there. Well, there's minus 15B, B, yeah, so hopefully it's just this section here, which is just a couple of ICs, hopefully just 3 ICs that might be responsible for pulling that down. So to try and identify which one of these components is responsible for that pulling down that minus 15 volt rail, I'm going to use the thermal camera. Well, I'm going to try anyway. So let's just get it over that section of the board there. Power supply is not on yet, and let's take a look at rounding this area here. So I'll just put power on now, and you can see immediately I've got two little hotspots there and there. That is specifically this op amp here, and lesser so this op amp here. So I've used the heat gun and I've removed the LF356, the one that was the hottest. So now we're ready for a power up, just to see what that minus 15 volt supply rail's doing. So we're ready to go, so let me go on the supply rail, which I can pick up over here I think. And power up. Yes, minus 15 volts on the button. That op amp's knackered. Now that's a high slew rate op amp. Not sure I've got anything like that in my stock. I'll have a look. Failing that, I'll just have to order one.